Hi everyone, welcome to Python tutorials where we are focusing primarily on image processing. Now in the last video we looked at random forest, XGBoost and LightGBM to understand which one is faster and what gives the most accurate results, and we realized that LightGBM actually is about 10 times faster compared to both XGBoost and random forest, and giving us very similar accuracy with XGBoost for sure, and better accuracy when it compares to random forest. So far, if you're interested in speeding up your training, we looked at model selection. Definitely LightGBM. But if you really want to focus on keeping your accuracy and not compromising any bit, XGBoost is great, right? So that's one lesson we learned. Now, how else can we speed up the analysis? We also looked at balancing the data in the past, right, to get better accuracy. We are doing all of these hopefully by not compromising accuracy, right? So we looked at balancing imbalanced data by downscaling or downsampling the majority class and upsampling the minority class. That helped us in actually getting much better overall intersection over union values and also accuracy for each of these regions or classes. So the one final thing I'd like to mention before moving on to deep learning topics is the topic of feature selection. Now, if you have thousands of features, training is going to take a lot of time, but then you can train with a smaller set of data, find which features are the ones that are actually working, and throw all the features that are not working and use those features to train your entire data, right? So for that, we are going to use a library called Boruta, B-O-R-U-T-A, and at a high level, this is the description. It creates shadow features. So you have these, let's say in our case, we have 41 features. It creates shadow features, and these are random features and shuffles the values in the columns. Okay, it creates this, and then it trains whether you want to use random forest or XGBoost. It's got to be a tree based because it's based on the built-in feature ranking functionality that random forest or XGBoost or any of these forest models, ensemble models actually have. So it trains on random forest or XGBoost and calculates this feature importance by looking at the mean decrease in Gini impurity. Okay. And it checks if real features have higher importance compared to the shadow features, right? I mean, the whole point of creating shadow features is now it can check, okay, are these real features? Do they have a higher importance compared to these shadow features after doing this operation? And then this repeats multiple times. And if original feature performed better than these, then it marks it as important. If the original feature doesn't perform better than these shadow features that it created, then the original feature is not important. That's what it's doing. And again, I recommend searching papers on this topic and then understanding it even better if you're really curious about how it's going to work. Okay. We are working with ready-made library. Again, these guys actually have a bit more documentation. I'm going to leave this link as part of the description so you can get more information about this. But I'll talk about how to install this, which is basically pip install. Okay, so now let's jump into the code and apply this Boruta approach on our data set that we have been working with in the past few videos, which is semantic segmentation. Okay, so let's jump in. And I should also mention that the first part of this code again is going to be same as what we are used to by watching the last few tutorial videos, which is again reading the data, extracting the features. I know this is, if you watched my previous videos, this is repetition nth time, but it's worth repeating it. Extracting the features, extracting or reading the masks, adding all of those together into a single data frame. Okay. And then let's continue from that point. Okay, so let's go through that exercise first. So let's go ahead and read the library, okay, the required libraries, and then read our images and extract all of our features using the filters that we defined here. And the features that we're going to use here are the pixel value itself, a few Gabor filters. And again, I'm generating about 32 Gabors, I believe. I bet of those 1 or 2 are useful. And I'm generating these 32 because I don't know what combination of sigma. By the way, Gabor is just a convolutional filter where it's a function of sigma, theta, lambda, gamma. I don't know what combination works well. That's why I'm generating the whole bunch. Now I want to use Boruta to find out which one works so I can only use that one in future. Okay, so we'll get there in a second, but we now have a pandas data frame called image dataset with about 10 million data points. Let's do exactly the same with our masks. Well, we are not extracting features from masks, but we are reading each mask and capturing it into a data frame. The next step is to put both of these together into a single data frame called dataset. And the reason I'm doing this is so I can drop all the pixel values with a value of 0 from the mask, okay, not from our original, all the pixel values in the mask that equals to 0, because these correspond to the regions where I haven't labeled them. And again, I talked about this many times. These images, these masks are partially labeled, and unlabeled regions are given a value of 0, so I'm dropping it, which means now I'm only left with 372,000 pixels that are actually labeled, so I can use them for my training. Okay, now let's look at how many of these we have. If you look here, label 3, I have 154,000 pixels. Label 1, 114,000, label 2, 74,000, label 4, 28,000. So these are not balanced. Since this is the last video on the topic of traditional machine learning, let's do things the right way. Meaning, let's balance the data set and then proceed. Okay, so how do we balance it? I covered this in our imbalanced data video. So first we are going to use scikit-learn utilities like resample method right there. And I'm separating my pixels with values of 1, 2, 3, and 4 into different data frames. Why am I doing that? Because now I can augment each data set, or undersample or oversample. Augment is probably the wrong word. So I'm resampling each data set. I'm saying, okay, I have 154,000 pixels as part of my DF3, right? The label 3, but only select 50,000 of those at random, and my random state is 42. And then when it comes to label 4, I have 28,000, but randomly copy some of these and give me a data frame with 50,000 rows. That's exactly what we are doing for each of these right there. This should be pretty quick. And once this is done, now let's put all of these together into one single data frame, right? I split them into separate so I can kind of resample them. Now I'm putting everything back together. So now my data set resampled, you see up here, exactly has 200,000 rows, 50,000 for each class. And we can print that. We can see how many for each class, 50,000. So now my data is perfectly balanced. Okay, so this helps us in getting better accuracy for the minority classes. Okay, now again, this is something we have done in the past video when we talked about dealing with imbalanced data. So I'm going a bit faster. So now I'm extracting my x values and converting that into a NumPy array instead of a data frame. And now I'm defining my y values, which is basically the label values, right, from our masks, and converting that into a NumPy array. And then let's go ahead and re-encode our y values, because right now our y values go from 1, 2, 3, 4, right? I'm re-encoding them so they go from 0, 1, 2, 3, because intersection over union and some of the other libraries, when you say you're dealing with multi-class problem, they assume that your class, the first class, has a value of 0. Okay, that's exactly why I'm doing this. Otherwise, it's a completely optional step. Now let's divide our x and y into x test and y test. X test and y test, x train and y train, right? So this is pretty common. We have all our data ready. Let's go to the next step. Defining random forest. We have done this again before. So far, I'm not using any feature selection. I just want to show you that, okay, this is what we did. And now we define our random forest classifier with our estimators as 50. And let's go ahead and fit the model. I'm doing this so I can compare the accuracy between using fitting a random forest with all 41 and features, and fitting it only with whatever it says are appropriate. And I want to see what I'm compromising. That's exactly why I'm doing this. So let's go ahead and run this. Again, I'll pause the video. We know it takes about 1 minute to do this. We have done this many times in the past. So let me pause this and continue as soon as this is done. And that was a bit faster because I forgot that we are actually resampling to get only 200,000 data points, right? I mean, we're not using all of these data points, but still, I think this is about 25 seconds or something, 28 seconds. Okay, so now let's go ahead and fit this onto our test and go ahead and print the accuracy 96.9. That's not bad, right? Without balancing the data, we were getting 95 point something. So this is already an improvement right there. Okay, now let's go down and do our calculation. Again, we'll summarize this all at the end of it. So let's not worry about it for now. Remember the intersection over union for class 2 without balancing, we got 76% for class 2. By balancing the data, by balancing these classes, we actually got 87.4, much better improvement. So if you haven't watched my video on this imbalanced data, here is a quick summary, why it is very important, okay? So now, can we speed up the training by not losing quality of results? That's the question here. So let's take a step back, and now let's, instead of using all of the data, because we have 200,000 data points, right? In our X-train, we have 160,000 data points. If you use all of that for your feature ranking, it may be a bit slow. So I just want to take 5% of that and then just run my feature ranking or, our feature selection part, and then get a good understanding of what features are working and then fit the entire data. Okay, that's the plan. So first of all, to do that, I'm basically taking 5% of this entire X-train and assigning that to X-train Boruta, Y-train Boruta. I don't care about the remaining part, right? I don't care about the testing part because we are not going to use that. So let's run this. And at the end of this, you got X-train Boruta as 8,000 points. So I have 8,000 data points between all the 4 classes. It's enough to tell us what's working, what's not working. Okay, the more the better. But again, you'll be wasting your time if you put the entire data set to do in doing this exercise. Now for Boruta, if you remember from the presentation I just went through one single slide, you can use random forest or XGBoost to do your fitting. I don't want you to confuse this part with the actual random forest part that we did, right? The actual random forest part is actually fitting the entire data. This part I'm doing to find out what my best features are. That's it. Here, you could be using random forest. I don't want to confuse you by putting random forest everywhere. So I'm using XGBoost. Why not? So let's go ahead and import the right library and define my model right there. I just called it model. Yeah, that should work. And from Boruta, yeah, again, pip install Boruta. I'm not sure if I mentioned that. I should have, but to get this Boruta, go ahead and just pip install Boruta. I'll leave the details down in the description, but just go ahead and pip install Boruta. From there, import Boruta Py, B-O-R-U-T-A-P-Y with uppercase P. So how do you run this? Okay, first define the Boruta feature selection method, right? How do we define that? Okay, my feature selector is my Boruta Py using the model called xgb.classifier. Again, this could be random forest with 50 trees or however you define it. That's the model. Number of estimators, 200. Okay, number of trees, number of estimator 200s. Verbose equals to 2. So show me what's going on the screen. That's what this means. Random state just defined to certain number. Maximum iterations 20. Okay, you can do more iterations. Again, as you see, after the first 4, 5, 6, 7 iterations, you may not see anything. It keeps saying that all 41 features are important, but then it says that, oh, these features are not, these features are good. It'd be interesting to see on the screen how this works. Okay, so let's go ahead and run this line and then define our feature selector. Okay, this is just defining the feature selector. Now we have to apply that onto our X and Y values, just like you fit anything else. And let's apply that onto our subset of data. And this may be a bit slow. Again, I'll give it a few seconds. So you can actually see what's going on the screen. You see, after iteration 1 out of 20, all 41, it's saying, oh, they're tentative. They're not confirmed. They're not rejected. They're tentative. Pretty soon you'll see that, okay, some are confirmed, some are rejected. And all of a sudden, it's usually a big jump. Okay, so let's see. I think maybe after 8 or 9 iterations, it should actually get, yeah, right there. 6 confirmed, 25 rejected. It already rejected 25 out of my 41. Okay, and 6 confirmed, 25 rejected, and 10 are tentative. Now 6, 8, and 27. As you see, it's going through these iterations, and I encourage you to play with the number of estimators and number of iterations to see, how it's actually behaving. But this is good. Not that slow either. It's okay. There you go. So at the end of this, it's basically saying that, okay, 6 confirmed, 4 are tentative, 28 are rejected. So now let's go ahead and print which is accepted, which is not accepted of all of our 41 features. So it's going to give me true. The first one, it says, yeah, that's good. False, 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 false. Most of my Gabor is false. I hope at least one of these is useful. So let's go ahead and print the ranking so we can see which ones actually, again, here it says it's true because it's rank 1 right there. This is rank 26, 26, so this is false. Well, that may not be that useful. So let's write these ranks against the feature names. So let's go ahead and get the column names from our resample and map the column names against our feature ranking. So that's exactly what we are trying to do, and go ahead and print it. So let's print these so we can go through these and see which ones actually work. In my example, pixel value seems to be rank 1. It's very important, obviously. Pixel value always will turn out to be very important. Most of my Gabors are useless. Like I said, if one works, I'm happy. Yeah, Gabor 27, that one is working. Oftentimes, you don't know which one works. For example, if you're trying to segment stratified layers, for example, you have a layer 1, layer 2, layer 3, you can physically see that, okay, these are all horizontal layers. With Gabor, if your theta equals to 0 or 90, I forget, if the theta is aligned in that horizontal direction, then that is the one that works. Everything else doesn't work. To find that one, I mean, in that case, I know that theta equals to 0, but then I don't know what the sigma values or other values are, right? So Gabor is great, but then unfortunately, only 1 or 2 often gives you the best, performance in terms of feature extraction. Okay, so Gabor 27, let's keep it. And what else shall we keep? Sobel, Roberts, Canny Edge. Most of these edge detectors are useless. SHAR seems to be working fine. Pruitt, Gaussian with a sigma value of 3, Gaussian with a sigma value of 7 is useless again. And median with a sigma value of 3 is also, it says keep it. Okay. So I hope that makes sense. So now the next part is, okay, now that we know which ones work, which ones doesn't, do I have to rewrite my code to only do these features? No. The answer is, now you can actually transform your original data. For example, our original data has 41, right? If you look at XTrain, we have 160,000 rows with 41 columns. So of those 41, just pick the ones that are relevant. So that's what the dot transform actually does. So when we run that, if you look at XTrain filtered, you see that only 6 columns are left over after we drop everything that it suggested is as useless. Or not so useful, I should say. Let's obviously remember that you transform your test data and also future data exactly the same way. You extract the features and you transform them, right? So let's go ahead and drop these. And now my X test also has 6. That's it. Now I'm all ready to fit my model, whether it is random forest or light GBM or XGBoost, it doesn't matter. In fact, you can use exactly the same approach, for any of these. Okay, so let's stick to random forest because that's what we used earlier. So we can compare apples to apples. So go ahead and get random forest. Let's use exactly the same number of estimators, except in this case, let's only fit that on the on this filtered data. Okay, not the original, which means we have only 6 columns. And I don't even need to pause the video. Well, at least I hope not, because we only have 6 columns to fit in this case. So hopefully much faster than the 28 seconds that it took earlier. Okay, well, it's I thought this would be much faster, but but we'll see. With a lot of data, this will be this you'll see a significant difference. Okay, so it took 14 seconds, so about half the time compared to the last time. Now, how much of a quality did we compromise, right? We will compromise some quality because you're not fitting to all the data. So let's go ahead and predict on our X-test. Remember, predict on X-test filtered because X-test has 41 columns. Here you have 6 columns, right? 6 features. And let's go ahead and predict the accuracy. So our accuracy is 96.4. That's not bad. We have very similar accuracy as before. So let's go ahead and do all of this. And at the end of it, let's not even look at these numbers. Let's clear the screen so we can just print out, just like we have done in the last video, all of these values, values that we can use to compare. So first of all, Random forest execution time is 28 seconds, and with Boruta, it's 14 seconds, right? Which is understandable. And accuracy of random forest is 96.9, 96.4. So we did compromise a bit on accuracy, but the speed, 2 times gain is not bad, okay? And when it comes to intersection over union mean, 94.1, 93.2. Yeah, not that bad. And when it comes to individual classes, 94.1, 92.8, 87.4, 85.4. So we did compromise a bit on accuracy, but I don't think that's a lot, especially if you have hundreds of features. Sometimes you may have thousands of features that you are using to train your machine learning algorithm. This is a great approach. Okay, save time. Initially, you are spending time in understanding what columns, or what features matter. Of course, it takes time, but overall, if you're gaining, a lot of time in not training on all of your data and still not compromising, this is great. So it would be interesting. Again, I'll leave this exercise to you to use exactly this data with 6 features, but use light GBM. Now it would probably be done in a couple of seconds instead of even like 6 or 7 seconds, right? With all of this data. So you probably get, that's one way of improving the speed of your machine learning. Okay, for now, I would pause any of this discussion about traditional machine learning. A lot of you are asking about deep learning. So starting next video, I'm going to focus more on deep learning. I'll go from absolute basics, assuming you know nothing other than basic Python coding, right? Please brush up your skills on NumPy, pandas, and basic for loops, while loops, right? Handling images, reading images. As long as you do that, believe me, deep learning is easy. Deep learning is not as difficult as you think, as long as you understand certain terminology. So I'll introduce the concept of deep learning in the next video, and then certain terminologies in the subsequent videos. Eventually, you should be in a position to put together your own deep learning architectures, models, or at least use existing models, and solve your problems like classifications or image classification, let's say, or structured data classification. For example, you have a bunch of data in Excel format. How do you classify based on the features you have there? And semantic image segmentation, of course. Let's focus on that. Okay. So I know you love these videos, so please go ahead and subscribe to this channel. Please tell your co-workers or co-researchers and other students that you know of, because we are putting a lot of effort in building these tutorials for you guys, and hopefully you're benefiting from this. Tell us that you're benefiting by hitting the like button, leaving comments, and subscribing to this channel. Thank you.